Oh, hey, Dan number 2.
Dan number 1, I really need your help this time. If I don't pass this final, I'm going to fail survey of geometry and flunk out of BYU. I really need your help understanding the law of cosines.
I don't know, man. I'm kind of busy here. I already helped you once. I feel like you could figure it out on your own.
Come on, Dan number 1, please. Come on, it's Christmas time. Silent night and stuff. Come on, are you not your brother's keeper, especially at this time of year?
Fine, whatever. I can help you. But just this one more time.
All right, Dan number 2. Here's the statement of the law of cosines. That if triangle ABC is any triangle, then c squared equals a squared plus b squared minus 2ab cosine of c. So it looks awfully like the Pythagorean theorem, but remember that we can only use Pythagorean theorem with right triangles. And we haven't specified the triangle ABC is a right triangle. We've just specified that it's any triangle. You'll notice that this same formula actually applies in the Pythagorean case. When our angle C is a right angle, then we have c squared equals a squared plus b squared minus 2ab cosine of 90 degrees. The cosine of 90 degrees is just 0. So this is c squared equals a squared plus b squared minus 2ab times 0, which is of course all 0. And so we end up with the Pythagorean theorem. C squared equals a squared plus b squared. And so the Pythagorean theorem is really just a special case of this equation, which we've now generalized to be for any triangle. All right, so now we know that this works in the case when C is a right angle or when we have a right angle, because then it just becomes the Pythagorean theorem. So now what remains is for us to show that it's true for an acute angle at C and for an obtuse angle at C. Yeah, Dan number 2?
Yeah, Dan number 1. You look super different. Also, the board looks different. What happened? Why are we wearing different things, and why are the colors on the board different?
Okay, so you don't remember this, but we got kicked out of the MARB last night, and so we're back now the next day recording this next part. So we're going to start by assuming that C is acute. And actually, before we do that, we're going to establish a different relationship real quickly by dropping a perpendicular from A to side BC. You see, to this point, Dan 2, the only relationships we have come from having a right triangle. What we know about how to measure sines and cosines, as well as relationships between sides, we only have when we have right angles. And so, by dropping a perpendicular from A to BC, we end up with two triangles within our, making up our main triangle that both have right angles at this point that I've defined F. So, by the Pythagorean theorem, we then know that each side, the square of the sides summed, will equal the square of the hypotenuse of these smaller right triangles. So, for this one over here, we have CF squared plus AF squared equals B squared. We also know from this one that BF squared plus AF squared equals C squared. Now, what I'm about to do is going to seem pretty arbitrary, but just know that it's a relationship that we're going to use later on in the proof in both cases, both the C is acute and C is obtuse case. And what we're going to do with these two equations is we're just going to subtract each side from itself. So we're going to subtract BF squared plus AF squared from CF squared plus AF squared, and we're going to subtract C squared from B squared. You'll notice that AF squared appears in both of these, so those are just going to cancel out, and we're going to get CF squared minus BF squared is equal to B squared minus C squared. Now, we're just going to tuck this away for a little bit while we work on this acute case. Okay, so it certainly looks like F is between B and C here, which is useful because between this gives us a little bit of information about these different lengths of the segments CF and BF. We know that the whole segment BC must be made up of CF and BF. So we can write them in terms of each other. So we know that BC minus CF is going to equal BF. Now, Dan number 2, how do we know for sure that F is between B and C?
Well, I mean, they're between because they're obviously between. I mean, the F is like dead in the middle of B and C, right?
Yeah, so I mean, it definitely looks like they are. But think of a case when C is obtuse, like this. If we drop a perpendicular from A to the line BC, you'll see that it actually falls not on the segment BC and certainly not in between the two of them. And so we know that F is between B and C in this case, actually because C is acute. Okay, during editing, I realized that part of my video got corrupted, but I'm just going to splice this in here. So we have that CF is equal to that and BF is equal to BC minus CF. We also know that BC is equal to A by the way that we defined our triangle. So we have A minus CF equals BF. Our fancy equation that we found gave us the relationship that CF squared minus BF squared equals B squared minus C squared. It gives us a relationship between the sides of our subtriangles and the sides of our main triangle. So now we can just sub in these expressions that we have for CF and for BF. And we have B cosine C squared minus A minus this expression again, because that's CF, B cosine C, all of that squared is equal to B squared minus C squared. If we expand out this polynomial, we have B squared cosine squared of C minus A minus B cosine C times A minus B cosine C equals B squared minus C squared. If we FOIL that out, we have B squared cosine squared C minus an A squared plus 2AB cosine C minus a B squared cosine C equals B squared minus C squared. These two terms will cancel out, and we get negative A squared plus 2AB cosine of C equals B squared minus C squared. By just rearranging these, adding A squared over, adding C squared over, and then subtracting 2AB cosine C, we get C squared equals A squared plus B squared minus 2AB cosine C, which is the statement of the law of sine, or rather the law of cosines. Now let's work with the case where C is obtuse. So I've gone ahead and drawn an obtuse triangle with C being the angle that's obtuse, and I've drawn a perpendicular from A to BC and labeled that point as F. So we're going to go about a very similar process using very similar relationships to get this relationship as well. What was that, day number 2?
You know, I hate to be that guy, but I'm not sure how we're going to work with this because it looks like the angle C there isn't really connected to our right angle at F, right? I mean, it looks pretty different from our last case.
Yeah, you're right. This one does look a little bit different. And so you're right. It will kind of affect the way that we go about this. We're still going to start with looking at the cosine of C. But you're right that C is no longer acute. And it's no longer part of, at least this part of C is no longer part of a right triangle. But we see that this side of C on the side of F is part of a right triangle. And the same relationship that we had before holds here, CF over B. But because we're interested in this angle C, this relationship is going to hold, but we need to make it negative because we flipped it onto that linear pair. And so we have cosine C equals negative CF over B. The other thing that's different is F is clearly no longer between B and C. Since C is obtuse, F falls outside of the segment, and in fact we have C is between B and F. And so the relationship that we have then by between this is that this whole segment, BF, is equal to BC plus CF. Now we're going to make the same substitution that we did before and have BF is equal to A plus CF, which we had here. Similarly, up here, we're going to turn this into negative B cosine C is equal to CF. And now, if you recall the crazy fact that we had, that CF squared minus BF squared is equal to B squared minus C squared, we now, again, have a definition for BF and a definition for CF. So I'm going to erase all of this, and we're going to work with the new polynomial. All right, so subbing in for B and C, all right, so subbing in for BF and CF, we now have this relationship. And again, we're just going to expand things out. And so squaring negative B cosine C is just B squared cosine squared C, which looks awfully like what we had before. Again, we're now going to FOIL this out. And you'll notice as well, before we had A minus B cosine C squared. Well, now we have A plus a negative B cosine C, which is just the exact same thing as this before. And you'll recall that that ended up being A squared plus 2AB cosine of C minus B squared cosine squared C equals B squared minus C squared. Well, this is just the exact same thing we had before. These cancel out. We get negative A squared plus 2AB cosine C equals B squared minus C squared. And it's all coming together. Add over, and then subtract that over. And there you have it. We again have the law of cosines, this time for an obtuse triangle, or a triangle with an obtuse angle. And with that, we've now shown it for all three cases of a triangle. We've shown it for obtuse, acute, and a right angle.